Okay, so in this video, we want to begin our discussion of how to systematically integrate rational functions. And if you recall, a rational function is simply the ratio of two polynomials. So this is our question now. If we're given an indefinite integral of a rational function, so p of x over q of x dx with respect to x, where both p of x and q of x are polynomials, how can we systematically find these indefinite integrals? And that is our question. There are quite a few steps, and they may not be obvious at first, and maybe not totally clear, but in the next few videos we will consider more explicit examples, and hopefully things will become more concrete. But let's look at the first step. And we'll break down these problems into several little steps. So what is the first step? In integrating rational functions. Well, step number one is to use long division to rewrite this division into two parts. Now, if the degree of the polynomial p of x is strictly smaller than the degree of q of x, then the long division will return the exact same expression. But if the degree of p of x is equal to or larger than the degree of q of x, long division will return a different expression. And this is the first step. So if ever you integrate a rational function and the degree of the numerator is equal to or greater than the degree of the denominator, you have to perform long division. Well, suppose it is the case that degree of p of x is equal to or greater than the degree of q of x. So if we apply long division, we can rewrite p of x over q of x as, well, the quotient coming from long division, uppercase q of x plus. And if you recall, when you perform a long division, two things are returned. There's the quotient of the long division and also the remainder, uppercase r of x of the long division, and the remainder is over the same divisor, q of x. And if you recall, the long division gives you something that is important. The degree of the remainder is strictly smaller than the degree of the divisor. So I can write this, the degree of r is strictly less than the degree of our divisor, lowercase q. So that is the first step. So now, of course, when you integrate this, you will integrate its alternate form. Now, the integration over q of x is trivial, as q of x is a polynomial. So we only need to use the power rule. So the question becomes now, well, how do we integrate a rational function where the numerator has degree strictly smaller than the degree of the denominator? Well, this will be now step 2. But before we can integrate this part of the expression, we need to do something with q of x. What we have to do is the following. We have to factor our divisor, q of x, into a product of linear and irreducible quadratic factors. Now there is one question you should be asking here, right? What we're saying is we need to factor lowercase q of x into a product of either linear and or, there could be both, irreducible quadratic factors. So the question you should ask is, well, is this always possible? The answer is yes, but this is not a trivial fact. The truth of this result, that this is always possible, if you're given a polynomial over the real numbers, you can always factor it as a product of linear terms or irreducible quadratic terms. Why this is true is because of the so-called fundamental theorem of algebra, which says that over the complex numbers, every polynomial can be factored into a product of linear terms. And if you go back to the real numbers, it returns the following conclusion: linear terms and or irreducible quadratic factors. We won't go into the details as why this works out. If you are curious, you can go online and look up the fundamental theorem of algebra and see how we can take a decomposition of Q as a product of linear factors over the complex numbers, and then from this obtain a decomposition for Q into a product of linear and or irreducible quadratic factors over the real numbers. But for us, we'll take this for granted. So that's step 2. Then you say, well, what was the point of factoring Q into a product of linear and or irreducible quadratic factors? Well, this is because of step 3. Now the idea is to decompose a single rational function into a sum of simpler rational functions, and we will call these simpler rational functions partial fractions. And that is step 3. So decompose r of x over, and I will not write q of x, but I will write what is coming out of step 2, which is a factorization of q of x into linear and or irreducible quadratic factors. So I'll be a little sloppy here. I'll write over the factored form of q of x. So once we factor q of x, we want to decompose the single rational function as a sum of what's called partial fractions. And the idea is, if we can decompose this single rational function, which may be very complicated, into a sum of simpler rational functions called partial fractions, then we'll have more integrals to find, but they should all be simpler than the original rational function. So even though it looks like we're doing more work, every one of them should hopefully be tackable. Now you may ask, well, what does it mean to say decomposing our remainder over the factor divisor as a sum of partial fractions? Well, we will go into the details of this in our next video. And so for now, that's it.